Thank you. Thank you, Dima. And it's a great honor, of course, to be invited to speak at this conference. So what am I going to be talking about? Well, it's in a way a continuation with a bit of a sideways feel, I suppose, of Peter's talk. Namely, I'll be talking about quantum chaos. I'll briefly review what I understand as quantum chaos here, but the central ingredient compared to previous works is actually a tool that has nothing to do with quantum chaos per se. It's a tool from harmonic analysis, which I call Fractal Uncertainty Principle. I'll make a precise statement later, but roughly speaking, it says that no function can be localized in both position and frequency near a fractal set. All right, so the tools that are used in the proof, they'll get a different amount of attention during this talk. So I'll talk quite a bit about microlocal analysis, which is a mathematical theory underlying classical quantum correspondence. So that's what lets us relate the classical to the quantum side of the picture. Now I'll talk about hyperbolic dynamics, which is mathematical theory of classical strongly chaotic systems that I'll use. And then the Fractal Uncertainty Principle, the proof, uses a bit of fractal geometry and a fair deal of harmonic analysis, but I'm not going to be presenting a proof of it today. I'll list the ingredients. All right, so let's see. Okay, now it works. So here is the, let me state the result. Let me start by stating what the result actually is. So let's consider negatively curved surface. So my setting is going to be a compact, connected, oriented, two-dimensional Riemannian manifold of negative curvature. I had a discussion with one of my co-authors at some point, and I feel compelled to also tell it's nonempty. There was a long discussion whether empty manifolds or manifolds or not. But anyway, it's a negatively curved surface. There's a picture on the right. Why do we study negatively curved surfaces? In quantum chaos, because the geodesic flow on that surface is a standard model of a classically chaotic system. You have hyperbolic behavior, you have rapid divergence of geodesics if you perturb in a generic direction from each other exponentially fast. And because I'll be using microlocal analysis, I will think of a geodesic flow as a flow on the cotangent bundle, rather than the Riemannian geometry would think of it as a flow on the tangent bundle. Of course, the two are identified by the metric. Now, what's studied by quantum chaos? Well, these are eigenfunctions of the Laplacian. So here they are. You have a complete basis of eigenfunctions. I'll normalize them in L2. And why quantum? Well, if you consider a universe, perhaps not a pleasant one to be in because it's so unstable, but if you consider a universe where your entire universe is a negatively curved surface, then these eigenfunctions would be the pure quantum state. So I will use this loose connection to quantum mechanics as the talk progresses to justify why we care about results and why we call this thing quantum. So of course, our world is not a hyperbolic surface, but it's actually many real world systems exhibit chaotic or hyperbolic behavior, but it's not so easy actually to find a closed system that has a chaotic behavior everywhere. They usually have some mixed behavior, which makes it very messy. So what we do in mathematics is, well, at least in this corner of mathematics, we just stick to the very clean and distilled model of a strongly chaotic system that allows us to actually prove something without worrying about all the other pieces of the phase space where the behavior is different. All right, so here's the result. So the result is the following. Let's take a non-empty open subset of your surface. And then the theorem is that the L2 norm of the eigenfunction on that set is bounded below, so bounded away from zero, by some constant, which of course depends on the surface and on the set, but does not depend on the frequency. So it doesn't deteriorate as the frequency goes to infinity. So it's a uniform in frequency or in eigenvalue, lower bound on its L2 mass. If you think about it from the point of view of quantum mechanical interpretation, then you think that the probability of finding your quantum particle in some non-empty open set is positive and bounded away from zero as the energy goes to infinity. All right, so here are the appropriate references. So in the case of constant curvature, so in case of hyperbolic surfaces, this was done in joint work with Jin, relying on joint work with Zal and Fractal Uncertainty Principle that was proved in joint with Woodward-Gens. And in the case of variable curvature that I'll try to explain, because this is more recent, why variable curvature is more difficult. So that was done in the work of Jin and Mon and Masha. All right. So I should also say that if you allow the constant here to depend on eigenvalue, then this bound is not new at all. This is just the unique continuation principle. And because once you fix lambda, this is just an elliptic equation that you're solving, and solutions of that cannot identically vanish in open sets, and is a quantity version of that. However, if you want a uniform bound, then you really have to use the geometry of the surface. So this is where the chaotic behavior of the geodesic flow will play a very important role. For instance, I don't think I have this on the slide, but if you took a round 2 sphere, then it's easy to see that you can have a sequence of eigenfunctions where this L2 norm will deteriorate exponentially fast enough. So the new result is really that this works in the high frequency limit, and that part does use the chaotic nature of the geodesic flow strongly. So here's a picture of the situation. So just like a comparison of two situations. One is completely integrable, and the other one is strongly chaotic. So on the left, the picture is this just a Dirichlet eigenfunction on the disk. So this, it's Bessel functions, right? But you see that if you plot a generic Dirichlet eigenfunction, it will look like that. So this is the plot of absolute value of this eigenfunction. And then you see that you have this white space in the middle. The diameter of the annulus will vary, but most eigenfunctions would have this white space in the middle, in which the L2 norm is actually exponentially small as eigenvalue goes to infinity. So the disk is an easy example that shows that this kind of uniform lower bound on mass cannot be obtained without imposing some assumptions, in our case, on the behavior of the flow. All right. So what's on the right? On the right, that's a picture courtesy of Alex Strohmeyer. This is a picture of a typical eigenfunction of the hyperbolic Laplacian on a hyperbolic surface. So you cut your hyperbolic surface into pieces, and you cut it along, and then you get this fundamental domain on the Poincare disk model, and that's the eigenfunction. So here you see that it really looks equidistributed. I'll talk about equidistribution a little bit more later, but from afar, so if you just look at the macroscopic features of this picture and let the eigenvalue go to infinity, it really looks like it's just everywhere. And in particular, there is no white space on this picture. Well, using Alex's color coding, there is no orange space because he coded 0 as orange for some reason. Right. So our theorem cannot show that you have equidistribution. That would be quantum inequality. But what we can show is that you cannot have white space of the type that you see on the left. All right, let's see. So okay, I see. All right, so now it turns out that actually in order to prove this statement, it's better to prove a stronger statement, which is a microlocal version of that, because using microlocal methods gives you access to the classical quantum correspondence. And so first of all, let me clarify the assumption, let me make a slightly weaker assumption on my surface. So all that you need is that the geodesic flow, it has the Anosov property. So here it's defined here. You have a decomposition of the tangent space to the sphere bundle into flow, stable and unstable directions. And you have exponential contraction along these directions, positive time stable, negative time unstable. Right, so negative recursive surfaces always have that. So that's what I mean by strongly chaotic system. But there are examples of surfaces which could have some positive curvature, but still have this Anosov flow. Now, how are we going to make it microlocal? Well, I'm going to use a quantization procedure. So if you start with any smooth, let's say compactly supported for simplicity function on the cotangent bundle, you can quantize it to an operator. So this goes back to this classical quantum correspondence. When you have a classical observable, then you can take the corresponding quantum observable, which is an operator, and so the features of the classical world somehow will correspond to the features of properties of that operator. Formally, the way you do it is you introduce a parameter h. I'll explain it in a moment, and then your function A is a function of x and psi. X is the position variable, and psi is the cotangent vector, which is in physics will be the momentum variable or the frequency variable for us as well. And so you just replace psi by the operator h over I times partial x. So you just take a function of these two operators. Now these operators don't commute, and you're on a manifold, so some work is needed. You cannot have a canonical procedure here, or you don't desire to have one, but up to lower order terms, it's canonical, and that's all that matters for us. So you can start with a function and get an operator. Now, what happens is, how should we choose h? So you can rescale the equation, and I prefer to view this eigenfunction equation rather than having a large eigenvalue. I want to have a small parameter here, and my h is going to be lambda inverse. So this is 1 over square root of the eigenvalue, and the reason is because you expect eigenfunctions to oscillate at wavelength h. And so, which is 1 over square root of the eigenvalue. So for instance, if you take this h over I partial x, you multiply it, you apply it to a function that's oscillating at wavelength h. When you differentiate, you'll get a factor of h inverse, and then this h exactly cancels this out. So that's the correct normalization for studying functions that oscillate at this h wavelength. All right, so here's a microlocal version of our theorem, which is, I'll explain how it implies the original version in a moment, but it's an estimate. So this is really what we prove. And what you have here, well, so there are a bunch of terms. It's an estimate for any L2 function. The left-hand side is just the L2 norm. So if it's normalized, it would just be 1 of the whole function. The error term on the right-hand side is something, and it's actually important what this prefactor is. But observe that if u was an exact eigenfunction, this would just be 0. So we just, our theorem doesn't just apply to eigenfunctions. It also applies to approximate eigenfunctions. That's basically what this error term says. And what's the first term on the right-hand side? Well, this is where in theorem 1, you would have the L2 norm of the restriction of your eigenfunction to a set. But what you do here is, instead of just localizing in position, you localize in position and frequency. And how you do it is you just take any symbol, so any function on T star m, which doesn't identically vanish on the cosphere bundle, and then you quantize it and apply to u. And so this first term on the right-hand side has the meaning of localizing to a potentially very small but still macroscopic set in the position and Fourier space altogether. So it's a stronger notion of localization. And we can estimate the total L2 mass in terms of the L2 mass of the localized function. All right, let's see. Okay, how does this imply the previous theorem? Well, if you take A, which is just a function of S, if your quantum observable doesn't depend on a momentum variable, then most quantization procedures would actually give you the resulting operator, just multiplication operator by A. So you get this bound for multiplication operators. And from there, you see, so by any non-zero function, and that's the same as just having a lower bound on the mass in any open set. And because you're estimating the total mass in terms of the localized mass, so this is the same as having a lower bound on the localized mass in terms of the total mass. And I should also say that this is sharp in 2 ways. One way is that if you assume that your symbol is identically 0 in the cosphere bundle, then it's easy to see using the basic semiclassical methods that the first term on the right-hand side would actually be O large of H. So your eigenfunctions, they live microlocally on the cosphere bundle. That's because we chose the correct normalization. We chose H as 1 over square root of the eigenvalue. And so if you try to localize away from it, you get something small. And here the theorem says that if you try to localize at any point near it, then near any point on the cosphere bundle, then you get a lower bound. And also, I should mention that the remainder, this log 1 over H over H, is sharp in the sense that if you relax it to, say, O little of 1, then there are counterexamples to statements of this form. All right. So I'll briefly talk about applications. I'm not going to state any theorems, but if you don't like eigenfunctions, then there are, there are implications of this for evolution equations. You can get control and observability for the Schrödinger equation by any nonempty open set. You can get exponential energy decay for damped wave equation as well. with any smooth, non-negative, and not identical as your damping coefficient. So that's something that you can prove using these methods that doesn't explicitly mention eigenfunctions. And there's also work in progress for getting a formula for how does this constant in the lower bound depend on the symbol taken or the set where we localize. You know, I often get questions about that, so I'll be happy to discuss that if there is a question. But there is some formula for it, so it's not maybe the most beautiful or the biggest bound you would hope for. All right. So now let me turn to connections to classical problem in quantum chaos that actually goes back to Professor Schnirelmann's work. So here is application to semiclassical measures. So semiclassical measures that were already featured before, I think they were called quantum variances in the previous talk, are a way to associate weak limits in the position and frequency space to a sequence of eigenfunctions. You know, as the eigenvalue goes to infinity, so you just take a sequence of eigenfunctions, let the eigenvalue go to infinity. Now you do not have any strong limit of that. That's easy to see, but you can ask for weak limits. Now the first thing you could ask is, how about I just take absolute value uj squared, and I just look at the weak limit of the corresponding probability measures. So that's something you could ask, but you could actually ask a more general question, which is these microlocal lists or quantum variances or semiclassical measures, which is the following. I say that my sequence of eigenfunctions converges weakly to a measure on the cotangent bundle if you have the following convergence statement. So for any test function, so for any classical observable, if you quantize this classical observable, so you get an operator, you really get a family of operators depending on h, and again, h is here 1 over square root of the eigenvalue. And then you apply to uj, then the limit you want it to be the integral of the classical symbol with respect to some measure, right? So this is a notion of a weak limit. You say that this sequence of eigenfunctions converges to this measure. So on the left, what is here, this is if A is a function, then this expression in quantum mechanics is interpreted as the average value of the classical observable A on the wave function U. That's the definition of it basically in quantum mechanics. And then you want to say that when you test your eigenfunction, or when you test your wave function by any classical observable, so you want to know the average value of the classical observable, then you will converge to the integral of this classical observable with respect to some measure. So such limits are called semiclassical measures. So you do not need, you don't always have a situation where there is only one semiclassical measure. So the whole sequence of Laplacian eigenfunctions doesn't always have a limit, but there is a compactness in there. So you can see that there's always plenty of limits. And in some sense, if you know all of these limits, so limits of all eigenfunctions, all high frequency sequences of eigenfunctions, then you know all possible ways in which eigenfunctions can concentrate, again, in a macroscopic sense, in the high energy limit. So it's certainly a worth a thing to study. So here are some basic properties of that. So first of all, each of these semiclassical limits turns out to be a probability measure. That's just related to the fact that we L2 normalized our functions. I forgot to say, but all norms are going to be L2 from now on. Its support is in the cosphere bundle. So this is another way of saying that your eigenfunctions live on the cosphere bundle. Now, where the classical quantum correspondence really starts entering is that you can show that these limits are invariant under the geodesic flow. So that's something you couldn't access on the base. You cannot access it as the weak limit of absolute value uj square Duval as a probability measure, but you can access it on the level of these microlocal lifts because the geodesic flow acts on the cosphere bundle. It doesn't act on the manifold itself. So then you ask, well, how many measures are invariant on the geodesic flow? And in most situations, the answer is lots. And so that makes the study interesting. So by itself, these two properties do not restrict much what kind of semiclassical measures you can get. So the natural candidate is the Liouville measure, which is basically the volume measure. If you have a sequence converging to the Liouville measure, then you say that your sequence of eigenfunctions equidistributes. So this means that the probability of finding your quantum particle in a macroscopic set in the position frequency and in the position momentum space in the limit is proportional to the volume of that set. So that's the best situation possible you could get. So that's the kind of thing that we saw in this pictures and hyperbolic surfaces a few slides later. Now, what's the worst thing that could happen from this point of view? Well, the most localized an invariant measure can be is a delta measure on a closed geodesic. And if you have a sequence converging to one of those, that's called scarring. And then there's plenty of stuff in between. So there's a very rich set of invariant measures under geodesic flows of the negatively curved surface. All right, so what does our theorem say about semiclassical measures? So here I just reviewed what the setup was. This is our sequence of eigenfunctions. Then we assume that it converges to some measure. Again, by compactness, you can also extract a subsequence that will converge to something. And then theorem 1 prime gives you a lower bound on this norm of eigenfunction localized by any observable which doesn't identically vanish in SRM. When you combine the things together with, I guess, a little bit of semiclassical analysis, you will see that what this tells you is that every semiclassical measure has full support. So every semiclassical measure, the measure of any nonempty open subset of SRM is positive. So that's what happens in the limit. So now here we have this uniform in frequency bound, uniform lower bound, and you localize to some potentially small set in position frequency space. And then when you take the limit of that in semiclassical measure, you see the measure of the set is positive, so you get full support. All right, so now it's time to discuss a little bit of history. This was already discussed in the previous talk, but I'll briefly talk about that. So the study of semiclassical measures was started really, I think the first statement that was proved for that is the celebrated quantum ergodicity theorem. So this is, in the West, US and then France, it was known in the 80s, but of course, the Russians were there first. So that's why it's often also known as the Schnirelmann's theorem. So what does it state? It says that you have density 1 sequence of eigenfunctions which equidistributes. So most eigenfunctions equidistribute. So if you plot an eigenfunction, if you plot a randomly chosen eigenfunction, it will look like it's just spread out everywhere in terms of these weak limits. So that's a great result because it's the proof is not very long, which is great, but the proof is very versatile. It only uses some basic tools from semiclassical analysis, such as Yegorov's theorem. It uses the von Neumann ergodic theorem. And it uses a little bit more, but it doesn't require particularly heavy machinery to prove it, which is great. And it's also versatile in the sense that the assumption you make here is very weak. You only need to assume that the Liouville measure is ergodic for the geodesic flow. That's it. So for instance, in our theorem, we assume that we have a negatively curved surface, which is a much stronger assumption than just ergodicity. And we assume that its surface is in dimension 2. Quantum ergodicity does not need such assumptions. But there is something left after this quantum ergodicity. It's something left to be desired because it only gives you something for a density 1 sequence. And that's a fundamental feature of it because it uses measure theoretic arguments, if you want, or averaged arguments on the phase space. So it can only access most eigenfunctions. It cannot tell you what happens for all eigenfunctions. So what do you do then? Well, there's something called the quantum unique ergodicity conjecture, which is that all eigenfunctions equidistribute. And that one typically comes with some stronger assumptions. I believe when it was made by Rudnick and Sarnak, it was for hyperbolic surfaces. It's reasonable to conjecture such behavior for any manifold with an Anosov geodesic flow, but there are examples actually where quantum unique ergodicity fails, even for strongly chaotic systems. They are not manifolds, they are quantum maps or things that are not strongly chaotic, such as the Bunimovich stadium. But there are cases where the ergodic behavior of the of the geodesic flow or whatever classical flow you have, where quantum unique ergodicity does actually fail. which makes it very challenging, because then if you want to prove it, you need to know what was wrong with these examples. What's so special about manifolds as opposed to, say, quantum maps, that you can still prove such a statement. So there is a family of cases where it's been proved. So it's been proved in the arithmetic case. So Peter, of course, gave a very extensive review of that. Here, I'm afraid I just wedged one result on my slide. But in the case of arithmetic surfaces, you have additional symmetries, the Heck operators, which you can exploit to get much more information, basically, about the measure. And these additional symmetries that let you show that Liouville measure is the only limit. Outside of the arithmetic case, this is really not known. So we don't know whether you know how to prove it, whether it's true or not. We don't know any of that. And you know, life has to go on. So quantum ergodicity has been proved a while ago, right? The last one was the case of boundary, Delitzsch-Zworsky in '96. And quantum unique ergodicity does seem to be out of reach in any kind of generic case. So what do you do in the meanwhile? Well, you say, okay, maybe quantum unique ergodicity was a bit too ambitious a thing to prove. So maybe we cannot show that the only semiclassical limiting measure is the Liouville measure, but maybe we can make some restrictions on possible semiclassical measures. For instance, maybe we can show that there is no limiting measure that's delta measure on a geodesic. And indeed, one can show that, and one can show more. So this comes in the form of entropy bounds, which are also mentioned in the previous talk, which is, it gives you, so those come, you know, from the work of Anantaram, and then later Anantaram and Nonempty, and there were a few other works in somewhat different settings. But what this tells you is it gives you a lower bound on the measure theoretic entropy of any semiclassical limiting measure. So in general, the result is a bit complicated to state, but if you have a hyperbolic surface, let's just say you have a hyperbolic surface, then the entropy of the Liouville measure for a hyperbolic surface would be equal to 1. The entropy of a measure on a, you know, delta measure on a closed trajectory for any manifold would be 0. That's 0 entropy. What Anantaram and Nonempty show is that the entropy is at least 1/2. So in some sense, they rule out half of possible candidates for semiclassical limiting measures. Of course, you know, it's a tremendous, huge, you know, infinite set of invariant measures. So that's, but they rule out, at least on this entropy scale, they rule out half. And what nobody seems to be able to prove for a hyperbolic surface is that the entropy is strictly bigger than 1/2. So that's not something that one can prove so far. And one reason is because one of the counterexamples, the Donenmacher for Dubiever example of quantum cat map, does have, you know, you have a situation in a toy model where you actually get the limiting measure of entropy exactly 1/2. So there's something, some new understanding is needed to push past 1/2 in these entropy bounds. Now, what does our theorem says? Well, our theorem says that this is a full support measure. Now, how does that relate to entropy bounds? The answer is it doesn't. So both of these results rule out delta measures. Neither of them proves QE. But there exist measures which are ruled out by one of these results and not the other. So in particular, since I'm advertising, you know, I'm advertising my theorem, of course, I will tell you that there exist measures with entropy as close as you want to the one of the Liouville measure, but with support, which is some fractal subset of S theorem, so not full support. And the other way around too. The other way is actually easier to construct. All right. So how do we prove this? Well, let me talk a little bit about the main tool, which is even though this is the main tool that makes the result work, it looks kind of detached from everything else. So on the bright side, if you zoned out for a moment, now is the time that you can pay attention for just this slide and then zone out again if you want, because this slide, the stuff in it is not currently related to whatever I was discussing before. So let me state the Fractal Uncertainty Principle. So I keep making this silly joke about the journal Chaos, Solitons, and Fractals, and maybe some of you remember the story of that journal. It's been a while now. But one takeaway from whatever the story was is that when you're talking about chaos solitons and fractals, you should define carefully what you mean by these words. So I already defined chaos. I said chaotic system has Anosov flow. Now, I don't use any solitons, but I do use fractals. So let me define fractals for you. So my definition of fractal will be very particular. I will only study them in dimension 1, and my definition will be porosity. So I'll say that a subset of the real line is nu porous up to scale h if for any interval of size between h and 1, there is a subinterval of relative size nu which doesn't intersect this set. So this is a quantitative version of saying that set is nowhere dense, right? What does it mean for a set to be nowhere dense? It means every interval on the line, every interval has a subinterval that doesn't intersect the set, right? That's the definition of nowhere dense. Now I'm just restricting the size of the subinterval. So for instance, if nu is equal to 1/6, I want to say that in each interval, I can find an interval of size 1/6 of that, which doesn't intersect my set. So a basic example of a fractal set which has this porosity property is the Mitherd-Cantor set. So that one is porous with constant 1/6. And you can play around with this picture and see that no matter where I draw my blue interval, I'll be able to find at least 1/6 of it, a contiguous piece, which doesn't intersect the Cantor set, which is in black. All right, so that's the definition of a fractal set for me. And of course, the thing here is that h is my 1/square of the eigenvalue ultimately, and that will go to 0. And I want my nu to stay fixed. So I want this porosity. That's why I mentioned things like 1/6. It needs to be some constant that doesn't depend on h. And you have to do it on scales from 1 all the way down to the wavelength scale, to scale h. So now what's the uncertainty principle here? Well, I can state it in this quasi-microlocal way, which is assume that you're giving two sets which are porous up to scale h with some constant nu. Then I'll study the norm of the L2 to L2 norm of the product of two localizing operators. One localizes you, the blue one localizes you to the set x in position, and the red one localizes you to the set y in semiclassical frequency. So I just took this is a this 1y of hi dx. This is a Fourier multiplier, but you rescaled it in frequency. So somehow you're localizing to high frequencies, at high frequencies. So each of these operators, of course, has L2 to L2 norm is equal to 1, unless one of x and y is never 0. And their product, however, that's what we show in joint work with Bourgain, that their product has L2 to L2 norm that's going to 0 as some positive power of h of the wavelength, where this power only depends on the porosity constant. You can restate it in a bunch of different ways. You can state it in a different way that assume that you had a function and you have a restriction on the Fourier support. You know that the Fourier support of this function lies in h inverse times this fractal set y. So it could be large because h is small. The Fourier support could be large, but it has to be distributed in some fractal way. Then when you take your function, you restrict it to another fractal set in x, then you will only get a small part of the L2 norm will stay as a result. And here's a remark, well, it's a technical remark that I'm hopeful I won't get to that part of the proof, but you don't need porosity you don't need porosity at all scales. In fact, what happens is if you think about how finely your sets have to be porous, then you see immediately that if you only require porosity down to scale h1/2 for both sets, then you're going to fail, because the Gaussian e to the minus x squared over 2h, it essentially lives in a bounded interval times h to the 1/2 in both position and semiclassical frequency. So this is the sharp case for the classical uncertainty principle. So if you want this porosity down to scale h1/2, then you cannot prove a statement like that. But once you get porosity just past that scale, then you can still prove this Fractal Uncertainty Principle. So that's nice. It's sharp in the sense that if you require porosity on two different scales, either it holds, or if this inequality is not satisfied, then it's easy to show that it fails, even the standard uncertainty principle. All right, so that's the statement. Again, as I said, I'm not going to say how it's proved, but it's using classical harmonic analysis. It has nothing to do with the rest of the talk. So instead of explaining how it's proved, I'll just use this tool as a black box, and I'm going to explain how to reduce to this tool. At least I want to show, to explain where do fractal sets appear in this quantum chaos question. All right, so here's the theorem that I'm supposed to be proving. It's this microlocal theorem. Now, for the purpose of presentations, I will make a few simplifications, some of them more egregious than others. First of all, I'm going to assume that we have an exact eigenfunction. I'm not going to assume how you get this. I'm not going to explain how you get this remainder. So then this is just, then what you have is just this bound of u in terms of h over u. Another thing that I do is I will allow myself to squeeze in a log 1 over h factor here. Now this is bad. If you get a result like that, that's a considerably weaker result than the one without this log, because your lower bound does deteriorate with frequency, cannot give you things about support of eigenfunctions, control, and so on. Luckily, it can be removed. So working harder, revising the argument that I'll present, you can really get a constant here that doesn't depend on the frequency. And that follows the strategy that was inspired by Nalinian and Taraman's original entropy paper back in 2008. And also what I'm going to do is I'm going to present list parts of the proof. I want to explain what happens in the variable curvature case, but for simplicity, I'm going to still present it in the hyperbolic situation where you have curvature -1, because then my constants get easier, because the thing that makes it nicer for constant curvature -1 is that the expansion rate of the flow is exactly 1 at all points in all directions. So I just know that I get e to the t or e to the -t when I propagate for time t, which makes presentation easier. And another assumption that I'm going to make, which is not egregious at all, is, so here I'm localizing u to some small set potentially in position and frequency using this operator a. I can easily arrange it so that this a is a cutoff function. Namely, I can easily arrange that this a, so I know it's not identically 0, but I can actually make it identically equals to 1 on some non-empty open set, and I'm going to call this set a whole. Okay. So you have this cold sphere bundle, which is a 3-dimensional manifold. You have the geodesic flow, which is chaotic, which acts on it. And now you have the eigenfunction. You think of this eigenfunction as somehow having some kind of distribution, mass distribution on this cold sphere bundle. So to define that, you need to really quantize, apply operators, take norms. And then basically I want to say that if my bound fails, then this function is going to be small. The mass of this function is going to be small on this specific open set called the whole. So that's the way I want to present this, that you have an eigenfunction, and imagine that this eigenfunction was small on some non-empty open subset of S star m. Can I get a contradiction for that? Or can I show that this function then would have to be small everywhere? So I'm just thinking, well, what would be a counterexample? Would be an eigenfunction which would have, let's say, very small mass in some set. Then I'm going to use microlocal arguments in the next page to explain how you get a contradiction from that. So this set u is going to appear a lot. The symbol a is really a cutoff function, which is 1 on u. All right. So how do you do that? Well, first of all, you don't want to localize to sets. Localizing microlocally to literally to sets, so things with boundaries, is nasty. Instead, what you should do is you should always, when you're actually doing proofs, you should always use cutoff functions. And so that's what I'm going to do. And in fact, because it's a microlocal argument, I'll quantize my cutoff function. So I take a partition of unity, A1 and A star. The star might become apparent close to the end of the talk. So but now let's just view it this way, where A1 is just my localizing to the whole, and A star is localizing to everywhere else, right? So in particular, the wavefront set of A star, which means the place where this operator lives in the position frequency space, doesn't intersect you. So this A star localizes you away from the whole, and A1 localizes you to the whole, but you have a bound on the norm of h over u, or that's what's in the right hand side. Now, the key tool that's used, and this part of the strategy that I'll describe until basically the end of this slide, is fairly standard. For instance, it is employed in Anand Taraman's paper as well, and in a way, well, it's some of it is used in the original, in the proofs of quantum ergodicity. So you need to exploit the geodesic flow somehow. And the way you do it is by taking the half-wave propagator. At least that's how I will do it. So you take this unitary family of operators, it's just the half-wave group associated to your Laplacian. And then, of course, if your U is an eigenfunction of the Laplacian, it's also an eigenfunction of this propagator with some eigenvalue, absolute value 1. And then what you can do is you can take any bounded operator on L2. So again, think of these bounded operators as quantum observable. So they localize you somewhere. You can take any bounded operator and you can conjugate it by this wave group. You again get a bounded operator. And as I'll explain in a moment, what's nice about this is that if the original operator was a quantization of something, then this conjugated operator would be a quantization of that something propagated by the geodesic flow. So somehow conjugation by the wave group corresponds to pullback by geodesic flow under this classical quantum correspondence. So for instance, if your operator A localized you to some small set, then the conjugated operator will localize you to the image of this set under the geodesic flow. And that will be important. Now, what is nice, however, is that if you take the, say, A1 of U, so that's something whose norm we really know, that's something bounded by the right-hand side. If you conjugate your operator A1, this op H of A, by the wave group, you will have the same norm applied to U. Right? So here you can see that, well, this just uses the fact, it looks like a trivial step, and it is mathematically, it is, but it's very important because this is actually the strongest place where we use that U as an eigenfunction of the Laplacian. As a matter of fact, once we have this step, I can forget that U was an eigenfunction of the Laplacian at all. That's where we use this. So what you get is you get invariance of U under the wave group, and because the wave group corresponds to the geodesic flow under the classical quantum correspondence, what you see is that the way the mass of U is distributed in the position frequency space has to be invariant under the geodesic flow. Now, this is a very dangerous statement to make because you cannot, there is a certain limit to this kind of propagation statements, and I'll explain it in a moment. You cannot do it just for all time. But what you can do is, now you can write your U. So previously I wrote my U as, let's say, A1U plus A star U, where A1U is something whose norm I control. So that's in the right-hand side. Now I can write my U as A star of TU. So any conjugated version of this thing that localizes you away from the whole U, plus O large of the right-hand side. Now, if you could do it just for one T, that would not be enough. No, A star would still have some norm. And then when you estimate, you won't be able to control this term. But you can do it for a bunch of times. And then, you can multiply, and then you get this estimate, which tells you that U can be bounded in terms of A minus A plus applied to U, plus the error term, which is, or plus what's in the right-hand side. And here I will do it logarithmically many times in H, and that's why I lose the log in this version of the argument. So how do I explain it from a quantum mechanical perspective? So imagine you have this high frequency eigenfunction, and it was small in the whole. How do you get a contradiction? Well, you say, okay, if it's small in the whole, so it means it's supported in some sense. Again, you have to do it using operators. One has to be very careful here. But let's say it's supported, in quotes, at the complement of the whole. But you also know that the way it's localized is invariant under the geodesic flow. So this means that this function is also supported at the propagation of the complement of the whole under the geodesic flow. Right, so this is really what's encoded by this product of operators. This product localizes you, and then you can do it a bunch of times. And so this product of operators localizes you to the places in S star M such that the corresponding trajectories were not in the whole for a very long time. So these are trajectories that spend a very long time not intersecting this whole U. So you know that your U can be written as something that's controlled by the right-hand side, plus you localize to all of these, to this relatively thin set. Okay. So, but here I'm very careful. So I cannot do this forever. So the classical quantum correspondence does break down. It's Yegorov's theorem that will tell you that conjugating by the wave group corresponds to pulling back the symbol by the geodesic flow. It breaks down. In hyperbolic case, it really seriously breaks down once your time is bigger than log of 1 over h. Because after that time, the symbols that you get, their supports will be thin in either stable or unstable direction, thinner than h, and just the classical uncertainty principle doesn't let you localize symbols with such thin supports. So you cannot localize to such thin sets. So what I'm going to do here is I'm going to go just up to that limit. So basically, I'll take my n's to equal log 1 over h. And I have to do this. If I go much less than that, I cannot prove a statement. And if I go much farther, the classical quantum correspondence breaks down. And then again, you know, you cannot get a handle on what these operators actually do. So here you have these localizations in forward time, so to trajectories which didn't go through the hole in forward time for time log 1 over h, and backwards in time for time log 1 over h. So these are these a minuses and a plus. And each of them you can make sense of as a pseudo-differential operator. You can really think of them as quantized observables. You can still think of these operators as localizing to some exotic looking but still bearable sets in S star m. That again are sets that, you know, where you didn't go through the hole for positive or negative times. But it turns out that together you cannot put them in a pseudo-differential calculus. You can multiply them as operators, but you cannot bring quantum classical correspondence to say that this product of operators will really be a quantization of the product of symbols. And in fact, there's an essential difference here, and that's where the new ingredient comes in, is that we will show that once you localize your eigenfunction so much that it's a minus a plus, it's actually small in norm. So this is not a place where you use an eigenfunction. The previous argument is where you use that, but now that you estimated your u by something that's in the right-hand side, plus this norm of a minus a plus q, you can actually show that the norm of the product of these two operators is decaying as the frequency goes to infinity. And so then you estimate your u by the right-hand side plus something that's small, which means that you can just move this term into the left-hand side and you're done with your proof. So the key thing is really how to show that when I localize to these thin sets in position frequency space, one corresponding to being forward, forward non-trapped, so not going through the hole, the other one backward non-trapped, how can you show that this localization is small in L2 to L2 norm? So this is where the Fractal Uncertainty Principle comes up. But before we get to it, let me show you what these sets look like. So here is a review. So here is the estimate that we need. And we have these two operators. And by Yegorov's theorem that I mentioned before, they are really localized to these two sets, which are the sets of points whose trajectories for a long time did not intersect the hole, forward or backward. So instead of proving anything about these things on these slides, I'll give you an example. So here is, I'm not going to use hyperbolic surfaces because that's a three-dimensional set and it's necessary to plot. So instead, I'll just for the purpose of these slides, I'll use Arnold-Catnap model for the pictures. So, the usual Arnold-Catnap, the hyperbolic toral automorphism, that's also an Anosov diffeomorphism. In this case, it has the stable and unstable direction. So the phase space then would just be the torus. And let's say my hole is just this disk in white. And then I'm just looking at points whose iterates under the Arnold-Catnap, either forward or backwards in time, do not lie in this hole. So currently I have time 0, so those three sets look the same. Then when I advance it once, I see that I have another white piece here, which corresponds to points which didn't lie in the hole, but when you apply the map once, they lie in the hole. And then when I keep applying this, so these are my gamma plus minuses. If you're using a cell phone, probably I should pause here. If you're using a bigger screen, your resolution will probably bear this picture. You get these two sets. And you see that these two sets have some interesting structure. They are smooth in one direction and fractal, i.e. porous, in another direction. And so you're trying to localize to these two sets simultaneously. You can reduce this question after some fair amount of work to the Fractal Uncertainty Principle. So you can, in this setting, you could try to rotate this picture by a certain angle to get sets, one of which would be localizing in frequency to a fractal set and the other one position to a fractal set. And then these two localizing operators would correspond to these localizing operators in the Fractal Uncertainty Principle that I showed before. And then you would get that this product is small and norm. So how do we do this? Well, here I'll just browse through this very quickly. So we have these two sets. And again, each of these sets is just thick enough that you can use microlocal analysis to actually quantize it to an operator. So you can really think of localizing the eigenfunctions to either the red set or the blue set, and corresponding to that are these two localizing operators, A minus and A plus. And we have the structure of these two sets, which I explained. So the directions you see here are the stable and unstable directions. So this is really where you use the chaotic nature of the flow, the fact that you have a stable and unstable decomposition very strongly. And then you try to rotate. You basically try to rotate this picture to use, you know, to get it to a fractal uncertainty picture. Now in variable curvature, this gets harder because the picture is not as clean as that. So let me very briefly talk about that. So the expansion rate of the flow is variable. So here you have all of these thin streaks, these thin stripes in these red and blue sets. They all have about the same thickness. They are lambda to the minus n, where n is the amount of time you propagated, and lambda is the, you know, the eigenvalue bigger than one of the Arnold-Cat map I used for the picture. Now in the real world situation, in constant curvature, it will still look like that. The streaks will be size e to the minus n. But in the variable curvature situation, they will be different thickness depending on which position you are. So here I have a model of a perturbed cat map, which kind of shows you what it would look like. So that's one challenge. And in order to do that, it means that when you did this propagation argument, you cannot choose your time constant. You have to adapt your time and to where you are in the space, which means you basically have to take a partition further and do more work there. And the second challenge, which is even more annoying, is that the stable and unstable foliations in the variable curvature case are not C-infinity. So you have to deal with that. And this means that quantizing these red and blue sets becomes instantly a lot of pain. So how do you do that? So you want to reduce this situation to that situation. And basically, in constant curvature, you could do it by taking a Fourier integral operator and just straightening out. That's what I meant by rotation. So you can really take an operator that would map, you know, the blue streaks to vertical lines, red streaks to horizontal lines, and it would be, you know, it would correspond to some smooth simplexomorphism. So that's something that that you can really reduce to that situation, which means that the Fourier integral operator, when you conjugate your blue and red operators here, you really get operators that look like localization, position, frequency, which is something that we can deal with. But in general, you cannot do this because the foliations are actually not infinity. And so the way you do it is you split your red set in a bunch of, you fatten out your blue set, you split your red set into a bunch of smaller pieces, which are spaced h to 2/3 apart. And then the fattening of the blue set is useful because then the red pieces, you know, the product of this fattened blue operator and the individual red operators that correspond to individual red pieces in this picture are almost orthogonal. So you can show that. And then by Kotler-Stein, this means that you can really reduce your situation just having one red piece and the second blue piece, because, you know, the triangle inequality really becomes a maximum in this you know, in this almost orthogonality business. And the way you do that is that the red piece is fairly thin, and the unstable foliation is not C-infinity, but it's C2 minus. So you use the fact that it has, well, at least strictly bigger than C1 regularity, which is true in dimension 2. And so what you can do is you can use this to just straighten out one unstable leaf that on which this red set is centered. And then you can straighten it out correctly so that the red pieces really become very horizontal and the blue pieces become relatively vertical, so that you can embed this red and the blue set in really just in horizontal and vertical rectangles, which makes it possible to actually access the Fractal Uncertainty Principle bound and finish the argument. And in order to make this rigorous, because as I said, you never work with sets in this business, right? You work with cutoffs, quantized cutoff operators. One has to use Egorov theorem up to local Ehrenfest time and long logarithmic time propagation of Lagrangian states, which is another kind of big tool in quantum chaos that was actually introduced also in Anand Araman's entropy paper, and we used the version from Nonempty 2019. Okay, I think finally I'm done. I'm not sure how long I was supposed to speak. Hopefully I didn't exhaust you too much. So thank you for your attention, and happy birthday to Professor Schnirelman, and here's to another 75 years of great mathematics. Thank you.
Thank you, Semyon, for a great talk. Are there any questions? Please unmute yourself for asking questions.
Yeah, I have a question. What about n-dimensional variable curvature higher dimension?
We don't know. Short answer, we don't know. Long answer, we don't know. But the reason is because it's kind of on this slide that if you have a surface and you have one stable and one unstable direction, and this means that when you remove the flow and dilation directions from the picture, in which nothing interesting happens, you really reduce this to this kind of one-on-one situation. So just Fractal Uncertainty Principle for one-dimensional sets. Now, if you wanted an n-dimensional manifold, you would need Fractal Uncertainty Principle in Rn-1. And that's difficult because it's false, as stated. And then this,
so to be clear, what's missing is the understanding of the analog of the fractional uncertainty.
That's right. So we don't know everything else. I mean, there is a bunch of other difficulties, but if you have a hyperbolic manifold, so you don't have the netness coming for variable curvature, then really that's the only missing component. Everything else should go through it as the same. What's funny is that one thing that I think we can prove, that's still work in progress, is you can actually show something for quotients of the complex hyperbolic space, which are more rare. And you would think that could be a harder thing, but actually it's easier because for complex hyperbolic space, you have a dedicated fast Lyapunov exponent. You have one direction which grows at rate e to the 2t, and all the other ones grow like e to the t. You can tailor the propagation time so that the slow things don't matter as much, and just use the Fractal Uncertainty Principle in the fast direction.
Yeah.
But in a generic situation, you cannot expect that such miracles would happen.
Thanks.
And let's say even in one dimension, would it be interesting to prove fractal uncertainty type result for a little bit more general operators than like 1x of x, 1y of?
Well, what do you mean by more general?
I don't know, but maybe it will not have any direct applications to eigenfunctions, but just as a statement and analysis.
So it's a curious statement in itself, right? And it's kind of funny that before these applications to quantum chaos, nobody actually apparently thought about that statement. So one of the many reasons it wasn't proved earlier is because nobody actually asked that question before. I should say that here it's stated in a harmonic analysis friendly way, but if you wanted to state it microlocally, you can, because, for instance, you can replace this 1x by a cutoff function. If the support of the cutoff function is inside of the set x, it just follows from the original statement, right? And you can do better. You can take two semiclassical two differential operators so that the symbol of one of them is in the x lies in x, and the symbol of the other one is in psi lies in y. And that's kind of more or less immediate. And of course, we use arguments like that because, again, our things are not literally. It's here. If you want to relax porosity, then this is difficult. You cannot just use the volume of the set. You can show that if you want to argue by volume alone, then this kind of statement would fail. So you really have to use some property at all positions, at all positions, at all scales, intermediate scales, or at least a big range of intermediate scales for this to work. I also should say that Professor Zeldich has had some interesting thoughts about how you can try to do it on the FBI side. I'm not sure it recovers the original principle, but you could try to convert it or write at least formally analogous statement for localization of harmonic functions in two different directions. Yeah. But microlocally, this is the yes. Yes.
Oh, pardon me. I didn't mean to interrupt you.
So there is, but as far as these microlocal applications go, this statement actually suffices for any 1D application. The rest is, there is work, but by cutting and pasting sufficiently enough, localizing, smoothing out, conjugating by Fourier integral operators, you ultimately reduce to that statement. And you have to, the problem is that you cannot prove this statement using microlocal analysis. It's anti-microlocal in nature. Just the statement stands against everything microlocal in a way. And so the reductions you can do using microlocal analysis, but once you're faced with the statement, you just have to do something different. And for something different, it is useful to have just localization, position, and frequency like that. All right, sorry. Yes, Steve.
I have a question. Is it possible to combine your theorem with Anand Tharaman and Nonen-Machart theorem and so forth to study the local dimension of the measures? You would have to take the measure of a ball of radius r and see how it shrinks with r.
So it's really two questions. One is what happens to the measure of a ball when you shrink, right? Because it's very tempting that, if you want to prove quantum inergodicity or something close enough already, or just something very strong already, all you need to show is the lower bound on the measure of a set is just the volume of the set, right? So we do get a lower bound here for, say, a small ball, but this lower bound is terrible. It's just terrible. If the ball has radius r, then some triple exponential, and so that's bad. And to add insult to the injury, if you have a collection of small balls, then the lower bound won't just depend on the total volume, right?
Yeah.
So that's one part. The other part is that in some sense, Anand Tharaman's original result follows partially that strategy, except once you get to the key ingredient, you estimate by volume. I didn't put it here, but if you knew that the volumes of your sets are much less than h to 1/2, you see 1/2 appears, and that's the half that appears in the, in Anand Tharaman's original bound, then you can get, then it's easy to prove this statement. If volume of x and volume of y is much less than h to 1/2, then the statement is trivial. You just start with L2, then it's an L1, L infinity type bound for the Fourier transform. And so this volume bound is in some sense what is used in those entropy arguments. But there's a bunch of other things that are used, like the entropic uncertainty principle. And even though it's called an uncertainty principle, so far we have been unsuccessful in combining the two and trying to get kind of a statement that's maybe best of both worlds. Certainly, we don't know how to prove that the entropy is bigger than 1/2.
Sorry, in the end, there was some estimate which was valid for all words. What words you mentioned?
Oh, somewhere. Which end? This one?
Yes.
Oh, that's
for each word, yes.
Oh, that's where I went a little bit fast. So the question is really, when you have these different streaks, what you want to do is you want to isolate. You want to say what's isolate those, and that corresponds to symbolic dynamics. So these different streaks, actually, what you do is you split your parameter space. You take a fine but fixed partition, and then you encode for each trajectory. You say at which with which set in the partition it was. And that to each point you have a corresponding word. And these different words, either for forward or backward evolution, would correspond to these different strokes, if you want, in this impressionistic painting. So then you can use this to split your operators into a bunch of things, corresponding to each word. And that's what we do in the actual argument. And so that's the words that were required, or whichever the word is. Where were my words? Where was the last time I mentioned words? So that's why I prefer to talk about the picture and about the stroke. But of course, mathematically, you do not prove things by pictures, right? So there is some way to isolate that. I'm just trying to remember where the words are. Yes, and then when you have this red clusters, they again correspond to some collections of words. Yeah, maybe it's here. No problem.